All right, hello everyone. Today I'm going to tell you about an upcoming paper with Ben Heidenreich and Tom Rudelius, where we are going to strengthen the sharpened distance conjecture to a conjecture that involves branes so that the sharpened distance conjecture behaves more nicely under dimensional reduction. So the sharpening is going to generalize the sharpened distance conjecture and make it and actually be a stronger condition than just the sharpened distance conjecture. So if you have a moduli space and you start at some starting point A, and then you travel an asymptotic distance away from it to some different theory, theory B, a distance phi away. If phi is very large, then the distance conjecture of Auguri and vacua says that you will have a tower of light particles that get exponentially light with the distance phi, separating theory B from your starting theory A. The sharpened distance conjecture says that at least one of the light towers at theory B will be so light that it has an alpha that is bounded below by 1 over square root of d minus 2, where d is the number of space-time dimensions. And all of these statements I'm making are in Planck units. So this bound that we proposed in 2022, so with Ben, Sami, Yue, and Tom, this bound had several motivations. One motivation is that it's a very special bound under dimensional reduction. If you assume that the distance conjecture has this bound, has an alpha above this bound, then this bound behaves in a very special way as you reduce your theory. You get very different behavior if the bound is lower than this. Of course, also, our bound is satisfied in many, many different examples, and is also fits very nicely with the emergent string conjecture. However, the sharpened distance conjecture is not automatically preserved under dimensional reduction. So the sharpened distance conjecture is only a statement about particles getting light in infinite distance limits. But if you put a theory with only particles, if you compactify a theory with only particles on a circle and make the circle small, then in terms of the Planck units of the lower dimensional theory, the particles of the higher dimensional theory will actually get heavy. So in order for the distance conjecture or the sharpened distance conjecture to be preserved under dimensional reduction, you need something to wrap the circle. You need branes in the higher dimensional theory, or strings, to wrap the circle to get light in the appropriate way for the sharpened distance conjecture to hold. So KK monopoles do get light, but they typically don't get light in a way sufficient for the sharpened distance conjecture to hold under dimensional reductions. So in this talk, I'm going to introduce the Brane distance conjecture. So this conjecture is a necessary condition in the string landscape for the sharpened distance conjecture to hold under dimensional reduction. It's not a sufficient condition. We still don't know a sufficient condition, but this appears to be a necessary condition. So this Brane distance conjecture in this talk, I will introduce this conjecture to you, and then I'll show you that it's satisfied in several examples. So here's this. Why it has to be nice under dimensional reduction? Well, I guess these swampland conjectures are observed to hold in each different space-time dimension, at least above 3. I guess I don't know of a necessary condition for every swampland conjecture to have to hold under dimensional reduction, but it seems that quantum gravity, or at least string theory, likes its conjectures to be held under dimensional reduction. Of course, demanding that something is held under dimensional reduction isn't, I guess one could try to look at conditions for a conjecture to be held under dimensional reduction and check that it's satisfied in the landscape, and that's what we're doing in this paper. Oh, thank you for the question. So the Brane Distance Conjecture, here's its statement. It's actually multiple conjectures in one. So we can pick a Pmax to be any integer between 1 and d minus 2, where d is the number of spacetime dimensions. So once we pick this Pmax, then we consider the set of particle towers or fundamental non-particle branes with at most Pmax spacetime dimensions. So when we're considering this set, then the Brane Distance Conjecture says that in any infinite distance limit, at least one particle tower or one brane from this set will get exponentially light, but with an alpha bounded below now by 1 over square root of d minus Pmax minus 1. I need branes that, at least when I wrap a circle or a torus, cycles of a torus, will give me a tower of winding modes. So I need at least that. So the Pmax equals 1 case, with the way this is worded, we're only allowed to consider particle towers. And the Pmax equal 1 case says that we have a particle tower with a mass, or I guess tension, that gets exponential light with an alpha greater than or equal to 1 over square root of d minus 2. So the Pmax equal 1 case is precisely the Sharpened Distance Conjecture. Were you going to ask? Yeah, so in this talk, I'm largely thinking about situations without potentials, and but potentially they could even change the Sharpened Distance Conjecture, maybe. So Pmax equals 1 is the Sharpened Distance Conjecture, but if we increase Pmax, that means we're allowed to consider additional branes besides just the particle towers. But since we're allowed to consider a larger set of particles and branes, we have a more difficult bound to satisfy. So this bound, this lower bound, becomes larger as we increase Pmax. In fact, it becomes really dramatic if we make Pmax all the way to d minus 2. Then this lower bound is just 1, which is a very large lower bound. It's dimension independent. So this is sort of where the power of the Brane Distance Conjecture comes in, or the some exciting aspect of it, is because often, for especially large values of Pmax, it can be quite non-trivial to find the brane that's getting sufficiently light. So I told you that this Brane Distance Conjecture is a necessary condition for the Sharpened Distance Conjecture to hold under dimensional reduction. I'll now explain how this bound here comes from the Sharpened Distance Conjecture in lower dimensional theories. So suppose we toroidally compactify a capital D dimensional theory to a lowercase d dimensional theory. Now, in this lower dimensional theory, let's consider an infinite distance limit, but let's only vary the moduli of the higher dimensional theory. So let's have things like radions, shape moduli, maybe axions from gauge fields. Let's have all of those things fixed. Well, as we take this limit where we're only varying the higher dimensional theory's moduli, one can argue that the towers of light particles you will get will be from just two origins. One could be the particle towers of the higher dimensional theory, and the other origin could be branes of the higher dimensional theory that wrap cycles of the torus to give you winding modes in the lower dimensional theory. In either one of these cases, the Sharpened Distance Conjecture must be satisfied in the lower dimensional theory, and in either one of these cases, the tensions of, or masses of particles in the lower dimensional theory are proportional to the masses and tensions of the branes of the higher dimensional theory. So in fact, if you require the Sharpened Distance Conjecture to be satisfied in this lower dimensional theory, That requires that the branes of the higher dimensional theory, when you vary the moduli in the higher dimensional theory, need to get light via the sharpened distance conjecture bound of the lower dimensional theory. This condition actually turns out to be precisely the Brane distance conjecture being imposed on the higher dimensional theory, with Pmax being capital D minus lowercase d plus 1. Yes? So KK monopoles depend on only the tensions of those depend on the radion of the compactification. And we're holding the radion fixed. So we're only varying the higher dimensional theory's moduli. Similar with KK modes. There is an additional strange type of brane called an exotic brane. These are codimension 2 branes. They appear in at least examples not to affect this, but they might modify this story slightly for the Pmax equals d minus 2 case. Pmax equals capital D minus 2 case. Yeah, thanks. That's a good question. So some work is needed to argue that these are the only kinds of particles, or the only, that the sharpened distance conjecture in these kinds of limits is satisfied by particles of these origins. You can do some gymnastics, which we do in our paper, and for instance, argue this from the emergent string conjecture of this paper, and then some analysis from this paper where they show that in dimensions less than 10, emergent string limits are accompanied by KK modes that are at the string scale. All right, so this is the argument for the Brane distance conjecture under dimensional reduction, following from, or as a necessary condition for the sharpened distance conjecture under dimensional reduction. So let's see the Brane distance conjecture in some examples. To do this, it's convenient to promote this alpha in the Brane distance conjecture to become a vector, which I'll call an alpha vector or a scalar charge to tension ratio vector. These were the zeta vectors in the previous 2 talks, but I'm calling them alpha vectors here. So this involves taking minus the gradient of the logarithm of the tension, gradient with respect to the moduli. So for instance, if phi is a canonically normalized modulus and you have a tension that depends on the moduli this way, then this alpha is just a vector that points, then this alpha vector is just a vector that points in the direction where the tension gets smallest, fastest, and it has length alpha. If you have a flat slice of moduli space, then everywhere on this flat slice, you can have canonically normalized moduli. And if you are in a situation where the alpha vectors of all of the branes are constant, then the Brane distance conjecture is equivalent to the condition that the convex hull of alpha vectors contains the requisite ball of radius 1 over square root of d minus Pmax minus 1. So this idea was introduced for the particle distance conjecture in a nice paper by these authors. And there's a straightforward generalization to branes, or the Brane distance conjecture. So in the upcoming examples of the Brane distance conjecture, I will we'll have a flat slice of moduli space, and we'll have alpha vectors that are constant. And we'll just have to see that the convex hull of these alpha vectors contains the requisite ball of radius 1 over square root of d minus Pmax minus 1. So let's see that these convex hulls are enclosed. Let's start with 2B, string theory on a circle. We'll start with the Pmax equals 1 case. So in this case, let's consider the radion dilaton slice. So this is the radion direction. This is the dilaton slice. So if we make the radion get really large, so consider a decompactification limit, you have this tower right here, which is the tower of BPS KK modes. Down here, as you make the dilaton very negative, so you're going weak coupling and make the circle very small, you have these wrapped fundamental strings that get light. Down here, you have a tower of wrapped D1 branes over here. And sure enough, the ball of radius 1 over square root of 7, as required by both the Pmax equals 1 Brane distance conjecture, which is equivalent to the sharpened distance conjecture, this requisite circle is enclosed. in fact, with saturation. If we increase Pmax to Pmax being 2, the Brane distance conjecture says we need this orange circle of radius 1/6 to be enclosed in the convex hull. Now, this is not enclosed in the convex hull of just particles. You can see this orange circle slightly gets out of this convex hull. But since we're considering Pmax equals 2, we can consider branes with 2-dimensional world volumes. So we can consider now unwrapped fundamental strings and D1 branes. And sure enough, they enlarge the convex hull so that this orange circle is enclosed with plenty of room to spare. We can increase Pmax to 3. The orange circle slightly grows, but it's still enclosed. We also get a wrapped D3 brane that doesn't do anything or doesn't change the convex hull. Pmax equals 4. Though a requisite orange circle gets even bigger, but is still enclosed, we also get an unwrapped D3 brane, which doesn't change the convex hull. Pmax equals 5. The orange circle is still growing, still enclosed with room to spare. We also get wrapped D5 and NS5 branes that don't change the convex hull. Things get a little more dramatic with Pmax equals 6. And now, the requisite circle is this red circle of radius 1/2, and it is just barely enclosed in the convex hull. So the Brane distance conjecture almost fails, but it doesn't. It's saturated in these two directions. You also get unwrapped D5 and NS5 branes, which spoil the saturation in these two directions. You also get KK monopoles down here. For Pmax equals 7, we need a circle of radius 1 to be enclosed, this magenta circle. And sure enough, if we have the wrapped D7 brane of 2B string theory, it lies over here, and its S dual lies over here, and the requisite circle is enclosed, just barely, with saturation there and there, and there, and there. So there's a lot of structure to this figure and similar figures in other examples. I'll comment on the following saturation condition. It's been observed that whenever the sharpened distance conjecture is satisfied, so this blue circle touches the convex hull of particles, this is always an emergent string limit. So this means that whenever you have saturation, you always need an alpha vector of a string in these directions. You can argue, as we do in our paper, that this results in saturation of the Pmax equals 2 all the way to D-4 Brane distance conjecture not being allowed to be saturated. But you can argue then that the saturation of the Pmax equals D-3 Brane distance conjecture, so like here and here, is always in the direction of a codimension 2 brane alpha vector. This is just coming from this saturation for particle condition when you reduce to 4D. We don't have similar statements for saturation of the codimension 2 Brane distance conjecture, which is related to emergent string limits in 3D. Sorry, for which specific values? Values of P for which you get saturation. Yeah? Sorry, are you asking whether there's anything special about the directions for which you get saturation? The value of Pmax or the? Oh yeah, so when you get saturation for the particle case, you always get a 2 in the direction of saturation. For saturation of this red circle, it's always in the direction of a D-2. Yeah. So for Pmax is only allowed to be saturated Brane distance conjecture for Pmax equals 1, D-3, and D-2. So if the direction here, over here, for instance, is an emergent string limit, the direction of saturation here corresponds to an emergent string limit when you compactify the theory down to 4D. And the saturation here, 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 and here correspond to emergent string limits when you compactify down to 3D. So we've done similar analysis for 2B string theory on tori in 8, 7, 6, 5, 4, and 3D. We found that you only get saturation in the Pmax equals 1, D minus 3, and D minus 2 cases. You get saturation in every single example, perhaps not in the projection of the high dimensional convex hole that I've chosen to present to you all here. These convex holes are just projections of higher dimensional convex holes. The Brane distance conjecture is satisfied in every single example. So let's go to heterotic string theory. Let's choose a, so here we will need to analyze non-BPS branes. There's a convenient value of the axions or Wilson lines that make you not have to deal with sliding that Tom talked about. So I'll choose that. So we need, since we're going to talk about non-BPS branes, we need to break up the plot into various different duality frames where the non-BPS branes are long-lived. When we do that, we can start with a particle distance conjecture. Here's the wrapped fundamental string of heterotic string theory right here in the KK mode. You also need, using the type 1 string theory language, a wrapped F1 type 1 string, which is non-BPS. The requisite blue circle is enclosed in the convex hull for the particle case. For Pmax equals 2, we need a slightly larger orange circle. But now we have the unwrapped fundamental string of heterotic string theory, and also the unwrapped type 1 fundamental or type 1 string, which is non-BPS, and the requisite circle is enclosed. For Pmax equals 3, a larger orange circle is enclosed. Pmax equals 4, larger is enclosed. Pmax equals 5, larger circle is still enclosed. For Pmax equals 6, the Brane distance conjecture is just barely saturated or satisfied with saturation in 3 different directions. We also get an unwrapped NS5 brane. Here's the wrapped NS5 brane. This spoils the saturation in this direction. We also get a KK monopole there. For Pmax equals 7, the magenta circle needs to be enclosed. Here, from the type 1 language, we have a wrapped non-BPS D7 brane of type 1 string theory, but we have not identified the branes over here. So if the codimension 2, or Pmax equals D minus 2 Brane distance conjecture is satisfied, or the saturation condition for Pmax equals D minus 3 condition is saturated, or satisfied, the Brane distance conjecture, or the saturation condition, predicts the existence of potentially novel non-BPS branes over there, which is kind of exciting. Novel branes were predicted with cobordism reasoning very recently in heterotic SO32 and E8 times E8. Not all of their tensions were worked out, and they might lie here. Yeah. 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 Okay. I'm not sure. I don't know. I guess I would like them to wrap a circle or a torus down to 3D, maybe to give you an emergence ring limit in 3D. I think that's a great question, and I don't know the answer. I'd have to think about that. Yeah. That's a good question. Yeah. So I'm definitely really reluctant to talk about a codimension 1 brane tension. I think codimension 2 is okay, but there are subtleties, like the subtlety you just raised. Maybe I have very little time left. I'll briefly say that these branes here are potentially mysterious if they do exist. There are also, we might be able to constrain some aspects of their tensions. So there are lots of rules that govern these tensions, these alpha vectors. So we're going back to 2b on a circle. There's like, you know, these vectors seem to lie on a lattice, 6, 4, 2. There's also an instanton we could have there, so a 0. There are all these properties of, there's sort of this lattice property. There's left-right symmetry from S duality, up-down symmetry from EM duality. There's a lot of constraints that these alpha vectors seem to have to satisfy. So you heard today in Tom's talk about this taxonomy program for alpha vectors of particles. It turns out that you can, in some cases that we're still working out, these taxonomy rules for particles imply taxonomy rules for lengths of alpha vectors of branes and dot products of alpha vector branes in higher dimensional theories. So here are some of them. These potentially can further constrain the mysterious missing branes in heterotic string theory. Last taxonomy rule I'll tell you is it's also interesting to consider the mass scale of the brane. So divide the brane's tension by its space-time dimension and take minus the gradient of the logarithm of that. I'll call this a lambda vector. This is the alpha vector divided by p. So in maximal supergravity, if we consider these, for these branes, they are these red dots here. And interestingly, these lambda vectors lie on precisely the boundary of the species polytope. So what you get when you consider minus the gradient of the logarithm of the species scale in all different limits and take the convex hull of this evaluation. So this is a further constraining taxonomy rule. Here's a zoom up of the points that I just showed you. All right, so in conclusion, the sharpened distance conjecture in lower dimensions requires the Brane distance conjecture in higher dimensions. So the Brane distance conjecture says that at least one particle tower or brane of space-time dimension at most Pmax in an infinite distance limit gets light with this formula where alpha is bounded below by 1 over square root of d minus Pmax minus 1. The Brane distance conjecture is satisfied in multiple examples that I've shown you. One can further derive taxonomy rules to govern these alpha vectors of branes. And potentially, one can make predictions about novel branes, especially in cases where the branes satisfying these potentially taxonomy rules or Brane distance conjecture are difficult to find. So thank you.